This is Unit 2, Topic E. We'll be looking at derivatives of trig functions in this topic. We already know two of our trig derivatives, right? Of our main 6 trig functions, we've already talked about the derivatives for sine and cosine. But we haven't looked yet at the derivatives for the other 4, tangent, cotangent, secant, and cosecant. The reason for this is that we actually needed the quotient rules before we could do that. Here's how this would work. If we want to take the derivative of tangent x, by the way, notice a slight variation on how I'm using the Leibniz notation here. Instead of defining f of x as tangent x, I'm just directly saying take the derivative with respect to x of tangent x. So this is we call it a derivative operator, and what I'm operating on is the function tangent x. So I'm going to use it again. Take the derivative, d dx, of, and then I'm going to rewrite tangent x as sine x divided by cosine x. Just basic trig identity, right? All right. I can clearly see the quotient rule here, f on the top and g on the bottom. So let's see, f prime would be cosine x, and g prime would be the opposite of sine x. Let me just remind you of the quotient rule off to the side here. I'm going to go with gf prime minus fg prime over g squared. So the derivative becomes g cosine x times f prime, which is also cosine x, subtract f sine x times g prime, which is the opposite of sine x, over g squared, cosine x squared. All right. The numerator is actually cos squared x minus a negative, so plus sine squared x over cosine squared x. And this is one of our favorite trig identities, right? The basic Pythagorean identity. Cosine squared x plus sine squared x is 1. And one more trig identity here, the reciprocal of cosine is secant. So I could also write this as secant squared x. And that's how you'll usually see these listed. The derivative of tangent x is secant squared x. We could do essentially the same thing for the cotangent. For cotangent, we would have cosine x over sine x, so it's just the reciprocal. So the f and the g here are really just reversed. And f prime this time is the opposite of sine x, with g prime being cosine x. Once again, I'm going to put all of this into my quotient rule form. And my derivative turns out to be gf prime. I'm going to take a little shortcut here. Multiplying g by f prime is just going to give me a negative sine squared x. Subtract fg prime. Multiplying f and g prime gives me cosine squared x. And g squared is going to be sine squared x. Here, if I factored out negative 1, I'd have that sine squared x plus cos squared x, which is just 1. So maybe I should show that. So that's really negative 1 times 1 over sine squared x. And again, one more little trig identity. The reciprocal of sine is also known as cosecant. So I could write this as negative cosecant squared x. And again, that's typically the way that you would see it if you were looking at a table showing basic derivatives. So we got 4 of them done: sine, cosine, tangent, and cotangent. We're ready for secant and cosecant, the last 2. All right, as we just mentioned, secant and cosine are reciprocals. So I'm going to think of this one as the derivative of 1 over the cosine of x. And we're getting lots of good quotient rule practice here. In this case, f is just 1, and g is cosine x. So f prime will be 0, and g prime will be minus sine x. All right, let's plug in our quotient rule here. Write it out one more time. I always find if I write it out often enough, I won't forget it, right? Gf prime minus fg prime over g squared. So gf prime, cosine x times 0, minus fg prime, 1 times the opposite of sine x, over g squared would be cosine squared x. And of course that whole first term is just 0, and that becomes a positive sine x over cosine squared x. And although there are a number of trig identities that you could employ to make this look different, the one that we usually use here is we rewrite this as sine x over cosine x times 1 over cosine x. Notice that that's still sine x on top and still cosine squared x on the bottom. And then this becomes tangent x, and that is secant x. And again, that's the way you'll usually see the derivative of secant x written, as tangent x times secant x. Our sixth and last trig function, cosecant x, we're going to use almost the identical approach to. Cosecant is the reciprocal of sine. So I'm going to rewrite cosecant x as 1 over sine x. And one more time, we'll use a quotient rule here. F is 1 and g is sine x. So f prime is 0 and g prime is cosine x. And then we'll apply our quotient rule, gf prime minus fg prime over g squared. So my derivative is gf prime, and again I'm going to use little shortcuts here this time. When I multiply those together, I'm clearly going to get 0, minus fg prime is just going to be cosine x over g squared sine squared x. 0 doesn't really matter, I can ignore that. And then I'll split this up kind of like I did last time. I'm going to put a negative out in front, and then cosine over one of the sines times 1 over the other sine factor, which we could rewrite as minus the cotangent of x times the cosecant of x, which is the way this answer is usually written. So we now have derivatives for all 6 of our primary trig functions. They are all together in a little table here at the top of the page. And I might also take a moment to just mention that these are also found in your lists of formulas that you can use on tests, right? You have this little packet. It starts with the unit circle and the trig identities and things like that. The next page is a list of derivative rules. It's got our basic definition of the derivative, and then it's got a bunch of these derivatives that we've been finding. In fact, we've now talked about all of the derivatives in the first column. Again, even when you take proctored tests, you will be welcome to use this packet of information, so these don't necessarily have to be memorized, although I think you'll find that you get to know a lot of them just because you use them quite a bit. All right, so let's find the derivative of each of these functions in these two examples here. In number 1, I've got two terms which can be handled separately, right? But within the first term, I'm going to notice a product rule. So let's deal with the first term before I even worry about the second one. F would be x squared, and g would be tangent x. So f prime is 2x, and g prime is one of our new ones. The derivative of tangent x is secant squared x. This is a product, so we're going to go with fg prime plus gf prime. So the derivative I'm looking for, dy dx, is fg prime x squared times secant squared x plus gf prime 2x times tangent x. And notice I'm starting to just kind of look at these before I write them down so I get my factors in the order that I like to see them. That takes care of my product rule. And then I also have to take the derivative of 5 cotangent x. The derivative of cotangent x is negative cosecant squared x. So I'm going to get a negative 5 cosecant squared x. And by just kind of looking ahead a little bit on the signs, I was able to avoid having to rewrite that whole thing. One more. Here is clearly a quotient, so we'll have to apply a quotient rule to take the derivative of w. So f is secant t, and g, I'm going to write that as t to the 1/3 plus 2, making it a little easier to take the derivative. F prime, again, one of our new ones. The derivative of secant, just right up at the top of the page, is secant t tangent t. That's a lot of t's, so I'm going to throw some parentheses in there. I'm sure all know this, but remember, with any trig function, you must always include the arguments. You can never leave them off. So if the original function is secant t, both factors in the derivative, secant and tangent, both have the same argument, t. Don't lose track of those arguments. G prime would be 1/3 t to the negative 2/3, and then just a plus 0, which I won't bother writing. And my original this time is a quotient rule, so we're going to go with gf prime minus fg prime over g squared. Oh, let's see. Leibniz notation this time would be dw dt. And again, you can also use w prime. I'm just practicing this a bit with us. So gf prime, g t to the 1/3 plus 2, f prime, secant t, tangent t. Subtract f secant t times g prime, 1/3 t to the negative 2/3, over g squared. T to the 1/3 plus 2 squared. All right, as I look at this, there's just a couple of, again, fairly small simplifications that make this look a little bit nicer and be a little bit easier to use if I have to go on and use it in a larger problem. First of all, I don't like the fact that this part looks kind of sort of factored and this part's not, so I am going to multiply everything out. So I'll have t to the 1/3 secant t tangent t plus 2 secant t tangent t. And then I have minus 1/3 t to the negative 2/3 secant t over that denominator, t to the 1/3 plus 2 squared. Overall, this isn't bad. There's one small thing that can be kind of a pain. I do have a little bit of a complex fraction here, right? I've got the 1/3 of the numerator, and it's part of a larger fraction. So, and I'm going to call this kind of an optional step, I could go ahead and multiply top and bottom by 3, which would allow me to cancel out that denominator right there. If I'm going to do that, let me do a couple of one other thing at the same time, just to, again, show you an alternative notation. I also can notice that secant t is in all of these terms. So just for fun, let's go ahead and factor out secant t from that numerator. And then I'll have 3 t to the 1/3 tangent t plus 6 tangent t minus, here the 3's will cancel, so I'll just get t to the negative 2/3. And again, the secant t from all 3 of those terms was factored out. Denominator is going to be 3 times t to the 1/3 plus 2 squared. So we no longer have a complex fraction, and I just chose the factored form of the numerator this time. All right, that brings us to the end of section E.